If you study physics, you likely know the strict reputation of I.E. Irodov's Problems in General Physics. The textbook demands precision. Today, we are going to work through problem 1.95. Before we begin, let's correct a common typographical error found in many digital copies of this text. Often, the scan misreads the variables as the trig function cot or co. Make sure you correct this to the Greek letter omega multiplied by time, or omega t. Our objective is straightforward. We will take the provided parametric equations for a moving particle and use basic calculus to calculate the exact magnitude and direction of the force acting on it. Solving this problem requires us to map these abstract equations directly onto the force vector of the particle. Let's start the derivation. This animated diagram shows a two-dimensional coordinate plane. We can combine the individual x and y parametric equations from the problem text into a standard position vector, r, using the unit vectors I and j. Classical mechanics gives us a clear path forward. To find the force, we first need to know the acceleration, and to get the acceleration, we have to take the time derivative of this position twice. Step 1 is to calculate the first time derivative of the position vector, which yields the velocity vector v. Doing this pulls the omega terms out to the front of each component. Pay close attention to the chain rule here. Taking the derivative of the inside variables generates that omega, and the derivative of the cosine function creates a negative sign. This first derivative is your rigid foundation. A single missed chain rule or dropped negative sign here will result in a physical model that completely misaligns with the original coordinates. This whiteboard lays out the next step. We execute the second time derivative on our velocity vector to calculate the acceleration vector, w. If we factor out the negative omega squared from both components, a familiar structural pattern appears in the remaining bracketed terms. The terms inside the brackets are identical to our original blue position vector, r. We can substitute r back into the equation, leaving us with acceleration equals negative omega squared times r. By substituting the position vector r back into the equation, we establish a direct linear relationship between where the particle is and how it is accelerating. Now we apply Newton's second law, force equals mass times acceleration. We substitute our new acceleration equation into the formula, resulting in this red equation, force equals negative mass times omega squared times r. To isolate the specific magnitude of the force, we focus strictly on the absolute length of vector r. By using the Pythagorean theorem, the magnitude resolves to the mass times omega squared times the square root of x squared plus y squared. With the magnitude solved, we shift our focus to the direction of the force by interrogating the physical meaning of that negative sign. Look closely at this animated graph of the particle's path. The blue position vector always points outward from the origin, while the red force vector points in the exact opposite direction, constantly pulling inward from the particle back to the center. The negative sign indicates that the force is attractive. It is the mathematical confirmation that the physical object is continually pulled inward to the center as it moves. Here is the summary card displaying the final answers required by the text, the calculated magnitude, and the direction, which points strictly toward the origin. When position equations are built entirely on sines and cosines, they indicate a harmonic oscillator, visualized here by a tethered object in continuous rhythmic motion. We define this specific dynamic as a central force. The inward pull is consistently proportional to the distance, perpetually drawing the object back to the center. Using vector differentiation allows us to calculate the specific mechanics of motion from seemingly abstract coordinates. Apply this same step-by-step logic to your next Irodov problem.